So different topic is related to the congestion control is TCP fairness. And what it means, okay, let me just get back to our go back N that I was talking before. With the go back N, you just set up the N as a kind of fixed number for the pipeline, and if multiple senders using the same go back N with the same N, they kind of potentially fairly share the network resources because they have a pipeline of N on both cases, and that's N effectively defines how much utilization they can have on both sides. With congestion control, this N is a variable. And depending on how many losses one flow observed, which kind of actions the other flow was taking, this N can be different. And if N is one flow has N twice as bigger as the other N, then utilization of the network of one flow will be higher than the other one. And effectively, one flow will be unfairly using the unfair amount of bandwidth compared to the other one. So this is what basic idea of fairness, and there was actually Chiu-Jain invented this index to define how fair congestion control is to how fair resources are being used by one congestion control versus another congestion control, or one flow versus another flow. And what you can do with this kind of fairness, you actually can build some form of a diagram, and sometimes it's relatively easy to analyze the fairness of on this diagram. We can just only look at the two, but potentially we can build the multi-dimensional one. So let's consider this flow A, flow B, and in this case it's a bit rate, but you can also think of in terms of congestion window size, because it's kind of, there's equivalency between these two. And what can happen is, so there's still capacity of the whole network. Like if the two flows are sharing the same network or going to the same destination, they effectively will share the same capacity. So you cannot send more than A plus B in this particular case. There's a fair amount. So this is kind of a middle ground, middle point, meaning both flows are sending at exactly the same rate. And any deviation from this fair share would indicate some form of unfairness. And overload is something that is impossible to have, but for the purpose of congestion window, you can actually set congestion window more than you have available bandwidth, but which will effectively result in losses. That's kind of obvious thing. And underload, it means that your congestion window is less than what can be maximum. And it's not necessarily that the TCP will always use the maximum capacity. It's actually most of the time it's using less capacity, and I'll ask a few questions about that later. And the fair point is the fair point. So there's I want to show you two diagrams, one for the slow start, for the basic slow start, and one for the congestion avoidance. And just for the one simple proof that both slow start and congestion avoidance phases as defined for new Reno or for Reno, slow start, new Reno, and several others, they are fair to each other. So for example, if we have two flows operating in slow start mode, they will be fair to each other. If two flows operating in congestion avoidance mode, then will be fair to each other. And I try to kind of explain with a few formulas here is, let's say there is some kind of initial state. Doesn't matter, like one flow started, the other flow started at a different point of time. So there is some share at the initial stage, like say state of x0. So what's going to happen eventually, so every time both of the flows receiving the information, they will increase the congestion windows twice, so like exponentially increase every time for every RTT. And if you do some calculations, the slope will be actually the same one. So they will be increasing their share along this line. And you can just do these basic calculations. So eventually they will detect, so they will be at some stage here, and they will detect losses, and they will go to effective one. Effectively, this will be point of the synchronization, and at this stage they will start increasing along the equal fair share line, and they will effectively at some point get to this fair point, or like overshoot the fair point, detect losses, go back, increase, go back, and so forth. So that would be the basic approach of a slow start. Congestion avoidance is slightly different picture. because the increase is not exponential and decrease is not to 1. If it to 1, then it will be immediately, so for example, in this case, it will go from this one point to both of them detected losses, and then they drop to 1 and then start increasing. So this is not exactly the case. What happens is, I mean, if you do some calculations, but effectively what they do is they increase each RTT, they will increase by 1, meaning they increase by the same amount. So they will increasing along this fair share, the parallel to the fair share line. And they will increase. At some point, they will detect losses, and both of them will halve their congestion window. So they will get from this perspective, it will be half, and from this perspective, it will be also half. Maybe picture is not exactly correct. Oh, actually, sorry, half of this. Yeah, so this is the correct point. Then again, they will be increasing, decreasing, and they will be eventually approaching that equal fair share line. It will be not necessarily exact fair share line, but eventually they will be approaching it. So it's kind of fair from a perspective of congestion avoidance. If we consider slow start versus congestion avoidance, then the picture will be different, and those not necessarily will be fair to each other. Another comment I would like to make here is fairness regardless RTT. So I was trying to, every time I said the kind of fair loss detected, something is increased, I always use word RTT. And which means that if RTTs of two flows are the same, then they will behave according to the picture that I'm showing here. But if RTTs are different, then the time to react for the one flow would be different from for the other one, which means they will have completely different actions. So TCP, at least congestion avoidance and slow start, they are not fair for flows with different RTTs. So for example, if I have a flow that going somewhere in the United States versus flow that going to somewhere in Europe, and they at some point they share the same bottleneck link, then the flow that kind of going inside the United States will actually have bigger chances or have a bigger share of the network resources than the one that going with a longer RTT. So this is technically a big problem for TCP, and it has been in some parts fixed in some of the newer TCP versions, but it's still in existence in some of the cases. It may not be that a big deal if you have a large amount of resources, but still it's a bit of a problem.